Netherlands, and in the next tutorial I will explain you some network management principles. What I will do is to explain first the term manager, then the term agents, then the management protocols, and I will conclude with management information bases. The manager system controls the operation of the network devices, such as routers, base stations, printers, PCs, and so on. The managed devices are called agents. Sometimes the term agents is used in a more narrow sense, however, to denote the piece of management software implemented within the devices that provide the management information. In our example, we see only 3 agents, but in real networks, a single manager can easily be responsible for thousands of agents. The manager communicates with the agents via a protocol. There are many protocols the manager can use for such interaction. Examples include ping, traceroute, telnet or the more secure version SSH, but also the command line interface. Next to these generic protocols, there are also a number of dedicated management protocols. Of these, SNMP is the best known example. SNMP is standardized in the early 90s of the previous century by the Internet Engineering Task Force, the IETF. Since it is not easy to use SNMP to configure devices, around 2003 the IETF decided to develop NetConf, the Network Configuration Protocol. At the same time that SNMP was being developed, the International Standardization Organization worked on defining CMIP, the Common Management Information Protocol. This protocol has, amongst others, been used for managing mobile telecommunication networks. Yet another approach is WEBM, Web-Based Enterprise Management. WEBM is developed by the DMTF, the Distributed Management Task Force, and supported by various operating systems. A special kind of management protocol is syslog, which allows the agents to signal certain events to the manager. Syslog has been implemented within Unix systems since the 1980s and is nowadays standardized by the IETF as well. One of the tasks that managers perform is to monitor specific management data, such as the number of packets dropped on a specific interface. To retrieve such management data from the managed device, the manager uses a GET-REQUEST PDU. After reception of the GET-REQUEST PDU, the agent retrieves the requested information from within its device and sends this information back to the manager via the GET-RESPONSE PDU. Another task that managers can do is to configure a device by setting certain management variables, such as an entry in the forwarding table. For that purpose, the manager sends a so-called set PDU to the agent. Finally, agents may be able to autonomously signal certain events to the manager, for example, in case an interface went down or the device has been reset. In the first version of SNMP, agents could signal only a limited number of events to the manager using the trap PDU. In later versions of SNMP, the capabilities for agents to notify all kinds of events have been extended. For that purpose, a new PDU was introduced, the inform PDU, which is acknowledged by the manager, so the agent knows the manager is aware of the event. Let's now focus on SNMP, which is the most important management protocol for the Internet. An important goal during the early development of SNMP was to keep the implementation of agents as simple as possible. Agent functionality therefore remained limited and, as we have just seen, agents had only minor capabilities to monitor their own behavior and notify the manager in case of problems. As a consequence, the manager had to continuously poll the agents to learn their status using GET-REQUEST PDUs. It is interesting to compare this philosophy to keep agents as simple as possible to the philosophy behind CMIP. In the case of CMIP, agents should be quite powerful and able to autonomously inform the manager in case of problems. As opposed to SNMP, the implementation of CMIP managers should therefore be relatively straightforward. As discussed before, after reception of the GET PDU, the agent retrieves the requested information and sends this information via the GET-RESPONSE PDU back to the manager. In case polling is performed sequentially, the manager will now poll the second agent. And also this agent reacts by sending a getResponse video. Depending on the amount of information being requested, it generally takes in the order of milliseconds to retrieve that information from within the managed system and send the response video. There are agents, however, that have rather poor agent implementations and need hundreds of milliseconds or even seconds before being able to send the response. In our example, the manager now polls the third agent, but in case of larger networks, the manager may have to poll thousands of agents. Since polling may take quite some time, the span of control for a single manager will be limited. In addition, the manager will have to handle a lot of management traffic. Scalability is therefore poor, and if thousands of devices need to be polled, the tasks of the manager should rather be distributed over several managers. To distribute the management functionality of the original manager, a hierarchy of managers can be created. In such hierarchies, the top-level manager interacts with the intermediate or mid-level managers, which in turn poll the various agents. Intermediate level managers may be tailored to the polling of one specific type of agent, such as all routers, or generic for all kinds of agents. Within the IETF, the protocols and information for such management hierarchies have been defined by the Distributed Management (DISMAN) working group. Instead of sequentially polling all agents, the manager can of course also poll all agents in parallel. Care should be taken, however, to not generate too much management traffic at the same time. And, of course, we have to poll all agents again after a certain period, which is often a 5-minute interval. Polling goes on 24 hours a day and will therefore be responsible for the major share of all management traffic. This is the cost of simplicity as advocated by SNMP. For fairness, we must say, however, that with later versions of SNMP, agents have more capabilities to report the manager of certain events, thus reducing a bit the need for polling. The last concept we'll discuss in this tutorial is the Management Information Base, the MIB. MIBs are included in every agent and organized into so-called MIB modules. Some of these modules are implemented in every agent, since they hold generic information applicable to all devices, for example the IP address of the device or the time the agent is up. Other modules are only implemented in certain kind of devices, since they hold information specific for that particular kind of device, such as a forwarding table in a router or the toner level for a printer. The manager usually knows the MIB structure of the various agents, thus which management information is maintained by each agent. In addition, managers usually store previously retrieved management information to detect, for example, anomalies or to plot a router's outgoing traffic as function of time. Depending on the management framework being used, MIB information may take different forms. Let's now focus on the SNMP framework. In the SNMP case, MIB information can take the form of simple scalars, such as, for example, 64-bit counters or textual strings. In addition, MIB information can be structured into two-dimensional tables. Such tables are useful, for example, if the agent has several Ethernet interfaces and for each interface you want to record the number of received packets, the number of transmitted packets, as well as the number of in- and outgoing octets. Each row in the table will then hold the information for one specific interface. The standard called Structure of Management Information, abbreviated as DSMI, defines the precise syntax of all structures that